So what is a Boolean function? A Boolean function is an expression derived from finite number of applications of the operations addition, multiplication and complementation to the elements of Boolean algebra. This is also called a Boolean polynomial. For example, AB is a Boolean function. A dash plus B dash plus AB dash plus AB. This is also a Boolean function. A dash plus B dash is also a Boolean function. So in any Boolean algebra, B equipped with addition, multiplication and complementation, we know that A plus A is A. Means 2A is equal to A. A plus A plus A means A plus A is A, then again A plus A is A. So 3A is also equal to A. So in general, we can write that 2A is A, 3A is A, 4A is A means NA is equal to A, where N is any positive integer. Also, A into A is A, means A square is A. Again A into A is A, then again A into A is A, means A cube is equal to A. And in general, we can write that A raised per K is A, where K is any positive integer. Thus, we notice that in Boolean function, there is no multiple or power appear. Also, in any Boolean algebra, by a constant we mean any symbol such as 0 and 1. And this represent a specified element of B. And by variable we mean a symbol which represent an arbitrary element of B. Now what is min term? A Boolean expression of n variables x1, x2, xn is said to be a min term if it is of the form f1 x1, f2 x2, fn xn, where each fi xi is equal to either xi or complement of xi for all I equal to 1, 2, 3 up to n. This is also called a minimal polynomial. If there are two variables x1 and x2, then there are four min terms x1 x2, x1 dash x2 means x1 dash is complement of x1, x1 x2 dash means complement of x2, x1 dash x2 dash means complement of x1 into complement of x2. So we see that if there are two variables, in that case we have four min terms. So in general, there are exactly 2 raised for n min terms in n variables x1, x2, x3 and xn. A min term in n variables is an expression of the form fx1, f2x2, fnxn, where fi xi is equal to either xi or complement of xi for all I equal to 1, 2, 3 up to n. This is by the definition of min term. So clearly there are two ways of selecting fi xi. Either it is xi or it is complement of xi means xi dash for each I equal to 1, 2, 3 up to n. So we can select fi xi in two ways. This is for each I may be 1, it may be 2, it may be n. So in general, we can say that there are 2 raised for n different min terms in n variables. So this is the statement and this is the proof of this theorem. Now disjunctive normal form. A Boolean function in n variable x1, x2, xn is said to be in disjunctive normal form, or in short we also call it dn form if it is sum of min terms. In other words, a Boolean function in n variables x1, x2, xn is said to be in disjunctive normal form if the function is a sum of terms of the type f1 x1 into f2 x2 into fn xn, where each fi xi is equal to either xi or complement of xi for all I equal to 1, 2, 3 up to n, and no terms are same. And disjunctive normal form is also called sum of products canonical form. It is sum of products, means sum of this type of functions. So write the function in disjunctive normal form. So to write this function in disjunctive normal form, first of all we will simplify this function. Then we will check that each term should contains the number of terms equal to number of variables. Means here we have three variables x, y and z. This function contains three variables x, y and z. So each term should contain three variables. So if the number of variables is less than 3, then we will introduce 1 to reduce it into dn form. Because 1 is equal to, we know that sum of a term and its complement is always equal to 1, means a plus a dash is always equal to 1. If any term contains a number of variables less than the given variable, then we introduce 1, and then we can convert this expression into disjunctive normal form. So here we have xy dash plus xz complement plus x dash. So first we will simplify this expression. So this is xy dash plus xz dash plus x dash. So if we apply De Morgan's law to this expression, we know that in that case we will take complement of individual terms and we will replace addition by multiplication. So in this case it will be xy dash dash means complement of xy dash into complement of xz plus x dash. Again we have complement here, again we have complement here. So by applying De Morgan's law again, we will write complement of individual terms and we will replace multiplication by addition. So it will be x dash plus y dash and dash, means complement of y complement. So complement of y complement will be y, and this is x complement plus y. And for this complement of x is x dash, complement of z is z dash, and replace multiplication by addition. To apply De Morgan's law, we write the complement of individual term and replace the addition by multiplication and multiplication by addition. And this is plus x dash. So this is x dash plus y into x dash plus z dash plus x dash. And we know that a plus b into a plus c is a plus bc. So we will apply it here. So this is a plus b and a plus c. So it will be a plus bc, means x dash plus y into x dash plus z dash is equal to x dash plus y z dash. And this is plus x dash. Now by applying commutative law, this yz dash plus x dash can be written as x dash plus yz dash. Also we know that a plus a is a, means x dash plus x dash is x dash. So we are left with x dash plus yz dash. So we have simplified the given expression to get x dash plus yz dash. So this expression contains two terms. One is x dash and one is yz dash. But it should contain three terms in each of this. So in this first term, y and z are missing, and in second, x is missing. So here two terms are missing. So I have written 1 into 1. Here one term is missing, so I have written 1. Here y and z are missing, here x is missing. Because we know that a into 1 is a into 1 is a. So x dash can be written as x dash into 1 into 1, and yz dash can be written as 1 into yz dash. So I have replaced one by y plus y dash and another one by z plus z dash because here y and z were missing. And here I have replaced one by x plus x dash because here x was missing and y z dash. Always keep in mind if any variables are missing, then to convert it into disjunctive normal form, we will introduce 1 for the missing term. And then we can write, we can use a plus a dash equal to 1. So here y was missing, so I have written y plus y dash. Here z was missing, z plus z dash. Here x is missing, so x plus x dash. Now we can again simplify this. So it will be x dash y into x dash y dash. If you apply distributive law, x dash into y plus y dash is x dash y plus x dash y dash. And again applying the distributive law, we get x dash y into z plus z dash, means x dash yz plus x dash y z dash. For the second term, we have x dash y dash. So x dash y dash into z plus z dash. So x dash y dash into z, x dash y dash into z dash. Again here, x into yz dash, x into yz dash, x dash into yz, yz dash. Here dash represent the complement. So we notice that x dash yz dash and x dash y z dash, these two terms are appearing twice. So also we know that a plus a is a. So we will use it and we will write only one term. Also we are applying commutativity here. To rearrange the terms, I have written x dash yz, then I have written this term x y z dash here. Then x dash y z dash, this term, then x dash y dash z, this term here, and then x dash y dash z dash. So I have not written this term because this term is appearing twice here. So I have not written this term. X dash yz, x y z dash, x dash yz dash, x dash y dash z, and x dash y dash z dash. So this is in the disjunctive normal form or DM form. So we have converted the given function in this form. All the examples to reduce the given Boolean function into disjunctive normal form can be used following this method. Now what is complete disjunctive normal form? A disjunctive normal form in n variable which contains all the 2 raised to n minterms is called the complete disjunctive normal form. For example, if there are 2 variables x and y, so then 2 raised to 2 means 4. So it should contain 4 terms. So x into y, x dash y, x y dash, and x dash y dash. So the function f equal to xy plus x dash y plus xy dash plus x dash y dash is the complete disjunctive normal form in 2 variables. So a disjunctive normal form in n variable which contains 2 raised to n minterms is called the complete disjunctive normal form. So if there are 2 variables, it will contain 4 terms. If there are 3 variables, it will contain 2 raised to 3 means 8 variables, and so on. If each of n variable is assigned the value 0 or 1 in an arbitrary but fixed manner, then exactly one minterm of the complete disjunctive normal form in the n variable will have the value 1 and all other minterm will have the value 0. Let's see. Suppose we consider the complete disjunctive normal form in any variable x1, x2, xn. We know that it will contains 2 raised to power n minterms of the form f1x1, f2x2, fn xn, where fi xi is equal to either xi or xi dash, means complement of xi for all I equal to 1, 2, 3 up to n. Now assign the value 0 or 1 to the variable x1, x2, xn and select a minterm form, the complete normal form as follows. Use xi if xi is assigned the value 1, and use xi dash, means complement of xi, if it is assigned the value 0 for each I equal to 1 to n. Then the term so selected is then the product of n ones and contains at least one factor 0. If one factor is 0, then the product will be 0, hence it will be 0. Now one more result. Two functions are equal if and only if their respective disjunctive normal forms contains the same minterm. So to prove this, two functions with the same minterms are obviously equal. If they have same minterms, obviously they are equal. Now converse, if two functions are equal, then they must have the same value for every choice of values for each variable. In particular, they assume the same value for each set of values 0 and 1, which may be assigned to the variable. And so by the previous theorem, the combination of the values of 0 and 1, which when assigned to the variable, make the function assume the value 1, uniquely determine the term which are present in the Dn form for the function. Hence, both Dn form contains the same minterm. So it proves the given statement. Now next, to establish any identity in Boolean algebra, it is established here. To establish any identity in Boolean algebra, it is sufficient to check the value of each function on both sides of the identity for all combination of 0 and 1 which may be assigned to the variable. We have seen in the preceding theorems that a Boolean function is completely determined by the values it take for each possible assignment of 0 and 1 to the respective variable. It means the Boolean function could easily be specified by given table to represent such properties. If such table has been given, then the function in disjunctive normal form may be written down by inspection. So we simply look at the conditions where the function take the value 1, then the sum of corresponding minterm, where the function take the value 1, give the function. Although the function so obtained may not be in the simplest form. So we will explain this method in the next example. Suppose we want to simplify this Boolean function, which is given to be ab dash cd plus cb plus cd dash plus ac dash plus a dash bc dash plus bc dash d dash. Here f is equal to ab dash cd plus cb plus cd dash plus ac dash plus a dash b c dash plus b dash c dash d dash. In these three terms, c is common. If we take c common, a b dash d plus b plus d dash into c. In these three terms, c dash is common. So a plus a dash b plus b dash d dash into c dash. By commutativity, we can write c into, I have written c here because ab is equal to ba. Also a plus b is equal to b plus a. So we can write b plus d dash plus ab dash d. Here also C dash into, for this I have used, we know that A plus A dash B is equal to A plus A dash into A plus B. So I have written A plus A dash into A plus B, and this is B dash D dash. Also I have used commutativity. I have written C dash here. Now again applying this here, B plus D dash can be compared with A, and this with AB dash, then we can write A plus A dash into A plus B. I will use it here. So B plus D dash into B dash and B plus D dash into AD. I have written into B dash into AD by commutativity. So I have used this here. So B plus D dash into B dash, B dash is one term, and B plus D dash into AD. I have regarded B plus D dash as one term. Also A plus A dash is 1. So it is C dash, and it is A plus B, it is B dash D dash. Also B plus B dash is 1, and 1 plus D dash is 1. So this term is only 1, and 1 into A is always A. So we are left with C into B plus D dash into plus AD, and I have again used this property here, B plus D dash into A and B plus D dash into D. So here we have C into B plus D dash into A, B plus D dash into D. Again we have applied the same condition here, C dash, A plus B into B dash, A plus B into D dash. Also this is C. By applying the commutativity, we can write it as A plus B plus D dash. Again here D plus D dash is 1, and B plus 1 is 1. So this term is gone. So we are left with C into A plus B plus D dash. Also here B plus B dash is 1, A plus 1 is 1. So this is 1 here only. So we are left with C dash into A plus B plus D dash. Again A plus B plus D dash, A plus B plus D dash. This is common. So we are left with C plus C dash. But C plus C dash is again 1. So A plus B plus D dash. So we have used A plus A dash B equal to A plus A dash into A plus B, A plus A dash equal to 1, A plus 1 equal to 1 to simplify this Boolean function. One more example. For any A, B and C in Boolean algebra, the following are equal. Means A plus B into A dash plus C into B plus C, AC plus A dash B plus BC, A plus B into A dash plus C, AC plus A dash C are, all these expressions are equal. So first of all we will consider first one, A plus B into A dash plus C plus BC. Here again I am using the condition A dash plus C into B plus C is equal to A dash B plus C. I can also use it by applying the commutativity, means C plus B into C plus A dash is equal to C plus A dash B. But I have written directly, so A dash plus B, so A dash B plus C. So applying the distributive law, A into A dash B plus C plus B into A dash B plus C. So this is A dash B, A plus AC plus B into A dash B plus BC. Again A dash is 0 and 0 into B is 0. And this is AC. B A dash can be written as A dash B. So A dash B B, so this is B C. So A dash is 0, 0 into B is 0, this term is gone. So we are left with AC, A dash B B, B B means B, A dash B plus B C. So we are left with AC A plus A dash B plus BC. So this is nothing but B. It means A and B are equal. Now A plus B into A dash plus C. This is C. A plus B into A dash plus C. So by applying the distributive law, A into A dash plus C plus B into A dash plus C. So it is A dash plus AC plus B A dash plus BC. But A dash is 0. So AC plus, by applying the commutativity, A dash B plus BC. So it means AC plus A dash B plus BC, because 0 plus A is A. It means B and C are, B is equal to C or C is equal to B. Now next, AC plus A dash B plus BC can be written as AC plus A dash B. If we introduce 1 here, so A plus A dash into BC, because A plus A dash is 1 and 1 into A is A. So AC, A dash B, A into BC, ABC, A dash BC. So it is AC plus ABC. I have used commutative associativity, A dash B plus A dash BC. So we can write it as AC plus AC into B, and this can be written as A dash B into A dash B into C. And by absorption law, A plus AB is A. So if we treat as A, so A plus AB is A. So it is AC. If we treat it as A plus AC is A. So it is A is A dash B. So it is A dash B. So it means B and D are equal. It means A and B are equal, B and C are equal, and B and D are equal. It means all the 4 are equal. One more example, in any Boolean algebra, show that A plus B into B plus C into C plus A is equal to AB plus BC plus CA. We know that A plus B into B plus C into C plus A can be written as A plus B into B plus C into C plus A by associativity. So B plus and C can be written as C plus B by commutative law. Again, C plus B into C plus A can be written as C plus BA. So by distributive law, A into C plus BA plus B into C plus BA. Again, AC plus ABA plus BC plus BBA by distributive law. So it is AC. By commutativity, it can be written as BA can be written as AB. So it is A into B. So this is BC. BA can be written as, this can be written as BB into A. I have applied commutativity as well as associativity. A into A is A, B into B is B. It means AC plus AB plus BC plus BA. This BA can be written as AB by commutativity, and A plus A is A, means AB plus AB is AB. So it is AC plus BC plus AB. Again, by applying the associative law, AB plus BC plus AC. So this Boolean algebra, in Boolean algebra, AB plus BC plus CA is same as AB plus BC plus CA. Now, max term. A Boolean expression of n variables x1, x2, xn is said to be a max term or a maximal polynomial if it is of the form fx1 plus fx2 plus dash 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 plus fxxn, where fxi is equal to xi or its complement for each I equal to 1 to n. If there are two variables x1 and x2, then x1 plus x2 is a max term, x1 dash plus x2 dash is a max term, x1 plus x2 dash is a max term. Here it should be x1 dash plus x2. It should be x1 dash plus x2. This is also a max term. So if there are two variables, then we will have 2 raised to power 2 means 4 max terms, means x1 plus x2, x1 dash plus x2 dash, x1 plus x2 dash, and x1 dash plus x2. Now conjunctive normal form. A Boolean function in n variables x1, x2, xn is said to be in conjunctive normal form if it is a product of max term. In other words, a Boolean expression of n variables x1, x2, xn is said to be in conjunctive normal form if the function is a product of terms of the type f1 x1 plus f2 x2 plus fn xn, where fi xi is equal to either xi or xi dash, and no two terms are same. Conjunctive normal form is also called the product of sums because it is a sum. So product of sums canonical form. So find the conjunctive normal form of the function xyz x dash yz plus xy dash z dash and x dash y z dash. For this, first of all, we will write the missing terms because this function contain 3 variables. So there should be 2 raised to power 3 means 8 terms. But here we have only 4 terms. So to reduce it to conjunctive normal form, first of all, we will write the missing term and we will denote it by f dash. So missing term is, here we have xyz, x dash yz, xy dash z dash, x dash y z dash. So what are the missing terms here? One is x dash y dash z dash. It is not here. Another is x y dash z. It is not here. X y z dash. It is not here. X dash y dash z. So these are the missing term of this Boolean function. Now we will find its complement. We know that by De Morgan law, we will to find the complement, we will replace addition by multiplication and we will take complement of each term. So x dash y dash z dash dash plus, we have replaced plus by multiplication, x y dash z dash, x y z dash dash, x dash y dash z dash. So we have taken complement of this, complement of this, complement of this, complement of this, and replaced addition by multiplication. So complement of complement is the function itself. So it is f. So it is again we have the complement here. So to again take the complement, we will replace multiplication by addition and we will take the complement of each term. So complement of x dash is x, complement of y dash is y, complement of z dash is z. So x plus y plus z. Now complement of each term, x dash, complement of y dash, y, complement of z, z dash. I have replaced multiplication by addition. X dash, y dash and z. Replace multiplication by addition. X dash dash means x, y dash dash, y, z dash. So this is by using the De Morgan's law, and complement of a complement is the function itself, means element itself. A dash dash is a, and this is the conjunctive normal form of the given function. So what is the method? First of all, write the missing term, then take the complement and simplify, and you will get the conjunctive normal form. One result, every Boolean expression which contain no constant is equivalent to a expression in disjunctive normal form. Let alpha be an arbitrary Boolean expression without any constant containing n variables. It does not contain any constant. Now we will show that it is in disjunctive normal form. If alpha contains an expression of the form ab dash or a plus b dash, for some expressions a and b, Then by De Morgan's law, AB dash can be written as A dash plus B dash, and A plus B dash can be written as A dash B dash. If we repeat the same process, if required, and use the result x dash dash equal to x, we may reduce alpha to a form in which primes apply in only two variables. Now applying distributive law for multiplication over addition, and alpha can be reduced to Boolean polynomial. If for some variable xi or xi dash is missing in a term t of reduced polynomial, we can introduce the variable xi in t by replacing t by t into x plus x dash, because x plus x dash is 1 and t into 1 is t. So continuing this process for each missing variable in each of the term in alpha, and applying distributive law alpha, and applying distributive law, here it should be comma, alpha can be expressed in an equivalent form in which every term xk or xk dash for each k equal to 1 to n. Finally, the duplicate term of any in the reduced Boolean expression may be eliminated by using the result x plus x equal to x and x into x is x, and this completes the result. Means every Boolean expression which contain no constant is equivalent to disjunctive normal form. Thank you.